Hi everybody, this is a really lousy shot here. The lighting's bad and everything, but I'm doing this really quickly. I just have a little bit of time in the evening to do this. I want to issue an apology to all of you for the last video that I did on the Marantz 2240. We talked a little bit of theory about how a differential stage works on the input of that amplifier. We talked a little bit about some of the advantages of a constant current source. I really went through that too quickly. I edited it improperly, and I may have misled some of you. At the very least, I may have just caused confusion and not clarified some things. So I want to try to amend that a little bit. First of all, in order to understand how a differential pair works, we have to talk about the two different modes of signal that exist in it. One is the differential signal. This is the one that we're typically looking at when we're looking at the differential stage of an amplifier, differential amplifier circuit. Second is common mode. And we hear of, if you read about this, we talk about common mode rejection ratio. And it's a very important factor in a differential amp. And it's one of the reasons that it has such an advantage over just a standard Class A single transistor amplifier. And we're going to see some of the advantages in this video real quick. It's going to be a very quick impromptu video. It's probably not going to be perfect, but hopefully I can expand upon a couple things and make this a little more clear than it was. And we'll do a little demonstration. We're going to build up a quick little circuit. It is by no means perfect. It is the most basic least amount of components you can use to make a differential amplifier, so it will have some flaws, but it will give us a little bit of idea of how it works. At least you can see the idea behind it. And I think you're going to see one of the differences of using a constant current source as the tail versus a resistive load, and what that active load actually does. So let's quickly look at the circuit once again and try to see what's going on. All right, the first thing we're going to do is just look at that front end of that Marantz 2240 as an example. So again, we have the emitters are tied together, and because these are PNP, okay, just the polarity is going to be upside down from our experiment that we're going to do. But let's just keep that in mind. And this is your tail resistor, as they call it. This is called a differential amplifier or a long tail pair. And this is the tail resistor. So you have a positive voltage here. It goes through this resistor, which acts as a current source, okay? And this current source feeds these two transistors. These two transistors are then fed a negative voltage on the other side. Your input signals of both sides, okay, are going to be with reference to the common. The common is going to be the center point between the positive and negative supply. All right. You can do this on a single rail power supply, but you would have to create a virtual center point or a virtual common by taking two equal resistors. I'm not going to get into all that in this video. We're not going to worry about that. For what we're trying to learn, we don't need to know all that. The main thing you need to know is if I turn one transistor on and this one is not receiving any signal at all, then more current's going to flow through this side, through this resistor, and less current's going to flow through this side, through this resistor. But even with no signal on either one of these, there will be some signal flowing, or there will be some residual current. And of course, you have this resistor going from your base to the common point. This is ground, this is common, this is not negative voltage. This is the negative voltage here. See, negative voltage, positive voltage, common down here. And this is going to pull this up, and you can see you have 0.1 volts in here. On this side, it's 0 volts. There's no signal being fed in here at this time. Although you will see a little bit of a signal in here from this bias circuit. This is your DC offset. and by applying a certain voltage to this, it will affect the difference between these two. So essentially, if these two have equal voltage or equal current flowing through them, there will be no signal between these 2 points. So if I took a meter and measured from here to here, I would read nothing. But if one of these turned on more than the other, then one side of this would become more positive than the other, and the other would be more negative than the other. And it would flip back and forth depending on which side is turned on. Okay, that's why it's called a differential amplifier. It looks at the difference between these two. Now they are both being fed by this single current source. So the total current is going to be this total current here, and it's going to be divided in between these two transistors. So this is going to be like a current divider, and that will change depending on the input signal. Now what we're going to do, and you can see what we're going to demonstrate, is we're going to show when you drive an input signal here, you're going to get an output down here, and that output will be amplified. But if I feed another signal into here that is in phase with this one, you'll see that this signal will reduce in amplitude, and if I put it out of phase, it will increase. Okay, so because the signals will add, and we're just going to see this. I'll actually demonstrate it. Now here's the circuit we're going to use, and it's just because it's so simple. These are a couple of 2N2222 NPN resistors or transistors. We're going to try, first of all, we're going to have your collector resistors are going to be, I believe, 10K. Okay, so we'll make these 10K resistors. And then we're going to try, first of all, we're going to test the output, the difference from here to here. We're going to put our oscilloscope in there and measure the output. And then we're going to try it with this 5.6K fixed resistance in there, which is going to be a fixed load. And then we're going to put an active load on here, which is the constant current source, and it's going to be a 2.5 milliamp current source. And we're going to see how it affects the output of this amplifier. Does that make sense? Now I'm going to kind of do this in a couple steps because, like I said, I've only had a little bit of time over a couple nights to do this in the evenings. So forgive me if the video kind of chops up a little bit. I'll try to edit it back together so that it all flows how I want it to go. But essentially what I'm going to do is we're going to see what happens if these transistors are a little bit out of match or any little thing, or these resistors are not right or something. We're going to find out how this constant current source can clean that up a little bit. Now another thing, at least that I find confusing, being the village idiot that I am, it's easy to get confused between op-amp theory and just very basic differential amplifier theory. Now remember, your basic diff amp that you see in a stereo, especially some of the vintage things that we work on here on the bench, it's based on this principle right here. And if you look, here's a very basic 741 op amp, and I can tell you the more modern op amps, the really high-end ones, have a lot more circuitry than this. But even at that, this simple little 741 op amp, look how many components are inside there. And it essentially does a similar thing to this circuit, but with a lot more refinement. If you look, here's your differential pair. Here's your tail voltage. But look at all the circuitry in that. And look at how much control you have over it. Okay, we're not going to talk about offset and all that. We do that with the resistors that go to the common point in here. But anyway, here's your plus and minus input, or your inverting and non-inverting. Okay, non-inverting, inverting. It's all there. But look at all this going on out here. So just understand there's a lot more to this than to this. So it doesn't always apply. And second of all, there are different ways to use this circuit. Okay? If you're using it in common mode or in differential mode, it's different. What we're looking for and what we're interested in is two different things. Same thing with, for instance, in this particular application, in this stereo, really, this transistor is acting like your basic Class A amplifier. So you have your emitter resistor up here. You have your collector with a resistor on it. It's a common collector circuit. Here's your output. You're driving your input base. Okay. However, since it is it's married to this other transistor in this differential pair, we can feed a certain amount of the signal controlled by this resistor. We can feed a certain amount into here, and it will counteract, it will either add or subtract, I should say, from this signal. Now, it's really important that these signals are perfectly in phase, or they won't cancel properly, and you'll get little artifacts. But for the most part, that's how this is going to work. So this is, if this were just a single transistor, you would have two resistors here at the bottom, right? You'd have one here and then another one going down and tying into here. And then your feedback would go into down here. And it would, again, it's like a passive circuit. It's not active like this one. So that's how we're using it there. But there's other, when you start talking about comparators and window comparators and all these things, completely different principle how you're wiring all this and using it from how you're using it in this amplifier. I just wanted to make that clear because I think I saw a couple comments and some of the things I was reading, while they were totally true, they didn't really apply to the application in which this is being used. So I hope that clears that up a little bit. Anyway, let's get to the experiment. Okay, let's try to do a visual example of what common mode current does in a differential amp versus differential signals. And what we're going to do is we're going to try it two ways. We're going to try it first with a 7.5K resistor as the tail resistor for our long tail pair. And then we're going to use a constant current source of 2.5 milliamps. We're going to compare the difference. Now I'm also going to put in line with these a milliamp meter, which is right here. And you can see I have this powered up right now, and I have plus and minus 15 volts. And the input that I'm going to put here is going to be measured with reference to the common ground. So the common is exactly halfway between plus 15 volts and minus 15 volts, right? Because it's a split power supply. We're now using this 7.5K resistor in the circuit. And actually it's not 7.5, I put a 10, I think there's a 10K in it. Sorry, 5.6K, let me fix that. I grabbed these components here and stuck them in here to give me a certain reading. Okay, here we go, it's 5.6K. Now when the amplifier is turned on and it's sitting idle, so there's no signal going into either of the inputs, the current going through the tail, you can see it's about 2.485 volts or milliamps. So it's pretty close to 2.5 milliamps, right? And if you look on the scope, there is absolutely no signal. So it's sitting idle. Now let's put a 200 millivolt peak-to-peak signal into this input right here. So this one is still going to sit idle. By the way, I have these tied to the common through a 100K resistor just to kind of pull them up a little bit. So if I turn on my 200 millivolt peak-to-peak 1 kilohertz sine wave, the first thing you'll notice is it went from 2.486 milliamps to 2.576 milliamps. So the actual current flowing through this has increased. That means that the total current flowing through these transistors has changed. And one transistor is actually driving harder than the other. Okay, because this one's actually has a signal going into it. We don't have any signal going into this. So if we take a look, this is what we have for an output. All right. And if we look at the current, it's gone up 2.577 milliamps. So as I said, more current is flowing through the tail. Now, watch what happens if I put a 180 degree, or I mean, if I put another equal signal onto this side. So now I'm going to put another 200 millivolt peak to peak in phase with this one, okay? And you're going to see what happens when we do that, okay? So now we'll have 200 millivolts here and 200 millivolts here, and they're both going to be in phase 1 kilohertz sine waves. So I'll turn it on, and then I have to align the phases. And you can see they're supposed to cancel out. If they're equal, they should cancel out totally. But if you notice, they don't. There is still a little bit of signal there. In addition, our current has gone up even further. And this is DC. It's taking the average DC current going through that tail. So now it's up to 2.598. All right. If I turn that second signal back off, so you see it goes up and down depending on what you do to the two signals. Now let's change it a little bit. Okay. I'm now going to move, I'm going to disconnect this tail piece. I'm going to shut off all the signals. And you can see it drops back down to 2.4. And then I'm going to connect it to this constant current source. So now, instead of having this 5.6K resistor, we have this 2.5 milliamp constant current source. And we can see we are at 2.53 milliamps, so it's about 2.5 milliamps. If I now put my 200 millivolt sine wave on this side and nothing on this side, nothing happens. This stays the same. The current does not change. And you can see this output looks the same, right? But if I put the second signal on and align the phase, look at that. Absolutely no common mode current signal coming through at all. It's completely flat because the signals are equal and the transistors have that fixed current in them. So there's no varying current at the tail. And you can see it's still 2.5 milliamps. That doesn't really move, hardly at all. Now this could change like, microamps because these transistors, as they run, they begin to heat up. And the same thing here. These will warm up and change their properties a little bit too. And this is what the whole purpose of this constant current source is. By regulating the current at the tail, we're not permitting excessive current to go through these transistors, so they can't heat up, so the VBE can't change, so the transistors will stay more closely into their linear operating region. Now it's not a huge deal if these are operating properly. In other words, if you're not driving these in their full range of the linear range of the transistors, you may not notice a big difference. But as you're driving the transistors harder and harder and getting closer to the edge of that of the linear range of the transistors, you could actually move into a distortion area where the transistors will distort and the signal will distort. So once again, this is what happens when I put two equal signals onto both that are in phase onto both transistors. There should be no output. However, if I turn it off, now I only have the left transistor turned on. I get that. If I go and I move back to the resistive load instead of to the active load, this looks the same, but when we turn on our second signal, you can see we get a little bit of stray signal there. And that's really the whole purpose of what a constant current source in the tail of a differential pair does. Now, here's another thing we're going to look at. Let's pretend I'm going to shut off this signal right here. Let's pretend this is your input coming from your tape deck or your record player or your input from the stereo, right? This is going to be your feedback from your power amplifier. So this will act as your global negative feedback. And if you look over here, I'll turn on the signal once again, turn on the second input, and I'll align the phase. And we're going to go over to our current source, right? So because they're equal, there's no signal there. But watch what happens if I start to reduce that second signal a little bit. See what happens? Now, this distortion here, this is a characteristic of the circuit that I have. In order for this to work properly, you may need to have either some emitter degeneration resistors or some other circuitry to clean that up. So just ignore that for now. This is just proof of concept. And you can see with 10 millivolts at the input, okay, so 10 millivolts here, 200 millivolts signal here, you have almost the full signal coming out. If I go to 20, 30, 40, 50, 60, 70, 80, 90, and as you go up, you see how it reduces the signal. That's how your feedback works on your amplifier. And if this starts to go the opposite direction, you're going to get positive feedback instead of negative, and it starts creeping up the other direction. See that? And that's an inverted signal. So that's how negative feedback works. So if you have 100% global negative feedback, you get a straight line. And if you just have a certain percentage, so here's 50% feedback, and you get about half the signal out. So that's how this differential amplifier works. Now on the other hand, we were looking so far at two signals that were equal going into, in other words, they were in phase. What happens if I make this signal be 180 degrees out of phase from this signal? What do you think we're going to get at the output? So we're now in phase. I'm now going to change it 180 degrees out of phase. And look at that. They add together. Okay. So you go from negative feedback to positive feedback, if that makes sense. So they become additive. So anyway, I hope that kind of clears up how a differential amp works, and also why you use a constant current source. All right, so let's go back to 0. I want to do this one last time. So there it is with the current source. There it is with the resistive tail. See the difference? Let me zoom you in more closely. Resistor, current source. Well, I hope our little experiment shed a little bit of light on how a differential amplifier works in its most basic form. There are literally entire textbooks written on differential amplifiers and op amps and the things that you can do with them. This was by no means an attempt to even scratch the surface, but what I did want to do is just kind of give you a little idea of what's going on and why I did what I did and tried what I tried on that 2240 amplifier experiment, and to show you some of the benefits that it may have. Again, I'm not telling you to run out and pull resistors out of your stereos and put current sources in. It's something you really need to plan, but you can see that if done properly, it can benefit in the ways that this little experiment showed. So I hope that helps, and if nothing else, I hope it was interesting to watch. It was certainly interesting for me to do. So as always, I wish you all peace, joy, happiness, and good health in your lives. And I really hope that clears things up, and I apologize if I caused any confusion with anyone. Stay well, everybody, and take care. I know I'm in for a big snowstorm coming in, so I may be snowed in, which may be good news for you, because if I can't leave for work, maybe we'll get some projects done on the bench. Until then, stay well, everybody. Bye-bye.